All right, I think if you're okay, Chris, we'll get started. Are
Sure.
you? Yeah. Okay. Let me introduce you. I'm sure everybody around the table here knows who you are, but briefly, it does give me great pleasure um, to open up this impact research seminar, and particularly to um, invite Chris to give his talk. You know, I've worked with Chris now for a number of years, and it's always been a pleasure. And it does give me great pleasure to invite him to give this talk. Chris is a member of a small team tasked with developing and operating a world-class biomedical and materials imaging facility at the Synchrotron. He's a senior instrument scientist supporting research which uses the imaging and medical beamlines on that facility. Chris started his research career studying gamma ray emission from the cosmos, and his PhD involved the development of a sophisticated satellite-borne gamma radiation telescope. The theme of radiation detection and its uses has continued throughout his career. And following that astronomy work, he then worked at a synchrotron unit in the UK, and again was focused on employing specialist detectors there. He came to Australia in 2006, initially at Monash, and led programs of research around instrumentation and medical physics at the new Australian synchrotron. He became member of the CRC for Biomedical Imaging Development and a member of the ARC-supported Centre of Excellence in Coherent X-ray Science. He, at Monash, has had been involved in a number of research projects, including small angle X-ray scattering to diagnose disease, methods of mapping small angle X-ray scatter signatures in volumes, the use of X-ray phase contrast for diagnostic imaging, using cell markers for tracking, as well as functional medical X-ray imaging. In the technical field, he continues to play an immense role in the development of X-ray detectors for clinical medical imaging on the synchrotron. So, with no further ado, it is a great pleasure to welcome Chris, and his topic is going to be "Got to Catch 'em All: Photon Counting Detectors for Synchrotron Medical Imaging." Thank you, Chris.
Thank you very much for the introduction, Patrick. Let's make sure I can share the screen here. Oh, no, hang on. Right, can you see that okay?
Perfectly, thank you.
Good, yeah, so thanks very much for the introduction. So as Patrick said, I started my career in astronomy, and we were looking at MEV photons from synchrotron sources, but the synchrotron sources in that case were quite a long way away. In fact, some of them were outside of our galaxy. The reason I'm mentioning this is because it was grilled into me as a student in those days that every photon mattered, that we had to collect every single photon that we could in order to get the science. And the reason is that the hero of my PhD thesis was a satellite telescope called COS-B, the Cosmic Observatory Satellite B. It was in flight and up in the air for 6.5 years in the mid-70s to the late 80s, and it collected a total of 200,000 photons in that 6.5 years. So that comes out at an average of about 84 photons per day. And of that, you know, most of those were background. So I'm just going to show you a quick slide here, if it'll work, that gives you the there we are, the picture of COS-B. This is the satellite on the right there. The detector that it used was a fairly old-fashioned technology. It was called a spark chamber, SC in there, and it used a high voltage applied between metal plates in order to visualize the tracks of photons that were coming down from outer space here, and the tracks would go down through this set of plates, and you would take a photograph of it basically in order to see where the photon was coming from. But nevertheless, in its 6.5 years, it surveyed a lot of our galactic plane, which you can see in the top picture there, and it did some really good science. So let me just switch to the laser pointer. And so I was very happy to follow on from that telescope with my own telescope that we made for my PhD, which was based on a slightly more sophisticated technology than that, but not so much. But of course, what we're interested in now is the application of photon counting detectors, not for space astronomy, but now for synchrotron radiation radiography. So the talk is going to be a very short history of two-dimensional photon counting detectors in general. It will be short, don't worry, I'm not going to bore you to death with all of that one. Some of the technologies that are used in these devices, because they are pertinent to the rest of the story. And of course, the pros and cons of photon counting, though it's not always the best type of detector to use, mainly for technological reasons. And of course, the focus in the latter part of the talk is going to be on our detector. That's the Synergy Impact detector that we bought for the breast and the airway imaging. Some preliminary results from characterization tests that we've made on that detector using the synchrotron, and then some future measurements that we're hoping to make later on. So what are we trying to detect? Your average 31 kV photon has a fairly short wavelength, which is good because it allows you to penetrate through most materials. It's got a very high frequency, which is not so good because that means that the stuff that Tim does, the phase detection, is incredibly difficult to do directly, 10 to the 18 hertz. So we're not going to be doing that anytime soon. And just to put it in context, the atomic diameter is about 0.3 nanometers, so it's substantially larger than the photon. And the photons have optical photons, which we're used to for imaging in cameras and things, have a substantially higher wavelength. And interestingly enough, as I was looking up some facts about this, the word photon was actually not invented until almost 100 years ago. 21 years after Albert Einstein was awarded the Nobel Prize for the photoelectric effect in 1926 by Dr. Gilbert Lewis. So in a couple of years' time, we will have a 100-year anniversary of the photon. So photon counting is an important part of high energy physics, and that's where a lot of the technology that we use for our detectors in general comes from. And that's because the experiments are very well funded, they're very large, and they require some really special technology to make them work. So the progress in our field, in the synchrotron radiation research field, usually relies on instrument developments in both high energy physics and astronomy. It's very rare that you have a detector development laboratory that's attached to a synchrotron source. It's not, I mean, the APS in Chicago has one, DAISY in Germany has one, but for a smaller synchrotron like ours, we tend to just buy the detectors from vendors or use collaborations to bring detectors in to do our work here. We don't actually develop them ourselves. So many of the big lab groups have photon counting detector technologies being made for high energy physics. And for the systems that are used in these tracker detectors, like you can see in the top right-hand corner here, they rely on building custom integrated circuits, which again is a fairly specialist area. And only the larger labs like the Argonne lab in America or the Rutherford lab back in the UK have the ability to do that, because it needs a lot of effort and a lot of very skilled people. Even more skilled is the idea of creating a circuit on top of which you then bond a material which will convert your photon into electrons. This actually really didn't happen until the 1960s, and it wasn't until the 80s that it started to become readily available in quotation marks at some expense, because the costs are very high for doing these things. And of course, detectors specialized for the synchrotron radiation research area is not a big market. So this is why we're having to piggyback on the back of some of these other pieces of science. And the business risks for creating a commercial version of these are quite high. But it's happened, as we know, and I'm going to explain why. And the main reason is that not imaging, but crystallography benefits greatly from these high technology photon counting detectors. And this was made clear to us back in 1981 when we had a conference in Europe to look at the future for X-ray detectors in synchrotron radiation. And at that time, the macromolecular crystallography community was burgeoning. They had a lot of interest from all sorts of areas to allow them to push forward the technology for making crystallography detectors that were much better than some of the things that we were using at the time. And I accidentally had a friend of mine who I used to work with at Daresbury in the UK come to the lab here yesterday, and we were reminiscing that in the early days, the crystallography detectors were actually packs of film. We had darkrooms in the outer hall there that would allow us to process the films in order to see the crystal reflections from the molecules. And of course, that was a very long and hard process. And this is the sort of detector that they really wanted in those days, something that would read out very rapidly, have small pixels, smallish pixels, 200 microns, and would be very sensitive. So that was then, and then there are other types of photon counting detector systems that we were working with. The one on the top right here is quite famous for me anyway, because I spent a lot of my time working on that in the UK, and it's a gas-based detector. It's a good detector for energies down at the sort of below 10 keV range, because the gases that were in it were argon and xenon, and they weren't terribly good at converting X-ray photons of anything of a higher energy. So to counteract that, we also tried using secondary electron emission photocathodes. So these are solid materials where the photon would interact in the material, but the electrons created by that process would escape. And then they would be amplified in the same way as these detectors amplified the electron cloud with fine wires and high electric fields. There are colleagues in the astronomy community also tried bolometers. If you cool things right down to liquid helium temperatures, you can actually measure temperature changes due to the individual photons hitting the detector. But these are quite tricky, as you might imagine, and they're not really suitable for synchrotron radiation research. There were some scintillator detectors that were single photon counting, so each photon produced a splash of light, so in the optical photon range, and the typical scintillators are the ones that we are fairly familiar with for medical imaging detectors these days, like cesium iodide and gadolinium oxysulfide. Materials that would conduct when the photon lost its energy in them were also very useful, and they still are. In fact, photoconducting medical imaging detectors are quite well thought of these days. And the last one, of course, which is the focus of our detector, is the semiconductor detectors. So these are semiconductor diodes, basically, with a reverse bias on them. And when the photon lands in the depleted layer in between the two electrodes, they create a puff of charge, which is pulled by the electric field towards an electrode, and then it's detected and amplified. So these are typically called direct detection detectors, and for the sort of energies that we want to do our radiography at, we can't use silicon very easily. Hasn't got a high enough stopping power, even with the thickest materials that are available. So we have to go to other sorts of semiconductors. And I'm just going to take a slight sideways branch here and tell you about a reasonably good success story that came out of the high energy physics community, which was the translation of one of their tracker type photon counting detectors towards medical imaging. The Medipix story is quite an interesting one because it's taken a long time to come to fruition. It started in 1997 with a detector that was designed for the inner tracker of, I think it was the compact muon solenoid, the CMS detector in CERN, with 170 micron pixels. And the guys there had this great idea of, wouldn't it be a useful detector for medical imaging? So why don't we try and spin it out and sell it? So they produced a collaboration of universities. In those days, I think it was only about 4 universities across Europe that would develop this detector and then use it for actually different things, but mainly for medical imaging. The second version of this was made in 2001, and it's actually still going. We can still buy Medipix 2 based detectors. You'll notice that the pixel size has dropped now to 55 microns. Medipix 3, which came a few years later, then added the option of having a timing capability, so they could use it for other sorts of tracking, again with 55 microns. And the newest version of this, Medipix 4, will really do spectroscopic X-ray imaging. So the real hairy goal of a photon counting detector is not just to count the photons, but to measure their energy as well, in which case you can do what a lot of people call colored X-ray imaging, or hyper spectral imaging. And TimePix 4 is aiming to provide this. It's a very difficult process, and as you can see from here, it's taken a long time to get to this point. So coming back to our detector, it's not based on the Medipix detector, Medipix chip. We did actually try during the initial phases of the project to look at Medipix-based detectors, but in fact, they weren't as reliable and easy to use as the detector that we chose. So even though this one has a slightly higher pixel size, we ended up buying the Detectors version rather than the Medipix-based version. The converter for this is cadmium telluride, which is, as I say, a high Z semiconductor, about 3/4 of a millimeter thick. Its pixels are 75 microns. We discussed at length with Tim as to whether this was a suitable compromise from the 55 microns. And I think at the end of the day, I think we made the right choice. The active area is 28 centimeters by 8 centimeters. So that's the sort of images that you'll be used to seeing from our imaging colleagues from the synchrotron here. One of the useful things about the detector is it has 2 thresholds which allow you to distinguish between photons of 2 different energies. And I'll explain that a little bit in a minute, why that's useful. What's not so useful is that the array has quite a few dead regions, and pixels which are twice the 75 microns at the boundaries of the chips here. So that's something we knew we'd have to deal with, and I think we've done a reasonably good job about that. But that's, it is one of the biggest problems. So for diffraction experiments on the synchrotron, this is not so much of a problem. The left panel here is showing you a typical small angle diffraction pattern. A lot of the information in this pattern is redundant. So as long as you don't get 2 reflections falling on any of these dark lines here, you've still got the information. And the dark lines are simply mechanical gaps in the detector array where you can't butt the modules in this case close enough together to bridge those gaps. So there's no information in those black areas here. And for radiography, that could be a problem. In radiography, we don't have redundant information. We want the information all the way through the object. In this case, it's one of our mastectomy samples. And so we're going to have to find a way of overcoming that. And as you know, we're working on that with mechanical and computer methods. So inside our detector, there is a hierarchy of chips and then panels of chips, which then form modules, and the modules form the detector array. So that's maybe explaining why we've got these different sized dead areas between the rows of the modules, the intermodule gaps, and the interpanel gaps as well. The one that we bought was a 3 megapixel 3x2 module design, and as you can see here, it's got about 3,000 pixels by about 1,000 pixels. We've engineered it into a nice protective box so that if by accident we have a bright X-ray beam shining on the front of it, it doesn't get blinded. This lid here is a 2 millimeters thick lead plate, so that it will stop pretty much everything that's going through it, but not all of it. It's quite possible to see X-ray beams going through that lead panel if you turn the detector on with the beam fully on it. It has tilt adjustment for rotation axis alignment with the rotation of the sample, and it also requires cooling, so we have some water cooling pipes and some dry nitrogen going into the back of the array here to make sure that when it gets cooled it doesn't ice up. And it's been working now for almost 2 years, and we've never had any particular big problems with it. So if I can get this thing to move forward, yes, here we are. So the data that comes out of that detector head, we specified that we required a 200 frames per second acquisition speed for it. So the digitization of the data as it comes out the back of the head here goes along these 4 yellow fiber optic cables, over about 20 meters of those, into a fairly powerful computer here, which will then take that information in and compile it into an image frame for us. On top of that, we have another fairly powerful computer, which is another 20 meters away in a locked room, which is where the medical imaging data is going to be processed. And this was a requirement of our security people here to make sure that any patient data that we have on that machine can't be accessed over a general network control. The PC, this black PC on the right here, which we call BCT Pro, has fiber optic connections to other parts of the beamline in order to talk to them during the acquisition process. And then within this PC, there is a file store. But in the early days, when we're still looking at non-patient data and we're looking at ways of processing it, we have a 10 gigabyte fiber optic connection to our main Synchrotron file store so that we can use the Synchrotron's own compute platforms to do some of the work. And the experiment control PC, which is not shown on this slide here, is yet another PC, and it will have access to a lot of the beamline controls, including the robot and the system that allows the robot to take the images. And we use an experiment control system called EPICS for that. So the cadmium telluride converter, which is the thing that turns the photons that we're collecting into puffs of electric charge, is a really tricky material to work with. It's taken many years for industry to provide materials of the right sort of quality to be able to make these sort of detectors. There were only 2 companies in the world that were doing this. I think maybe there's now only one. Because of the difficulty is to create defect-free crystals. Any defects in these crystals will come out as areas of inefficiency on the detector. So you'll get black marks and things. The other problem is that this has to be bonded to the integrated circuit underneath it, which contains the readout electronics. That, as I say, even though it's a reasonably mature technology for industry, is tricky to use for non-commercial scale type detectors like this one. So all hats off to Detectors and to the Medipix collaboration for getting that through. But the defect count is coming down with time as people work to try and make this material more defect free. It's improving, and the price is coming down as well. So I think that photon counting detectors made from this sort of material are going to be the way of the future. One of the issues for us especially is that the cadmium and tellurium have absorption edges for these 2 elements right within the radiographic energy range that we're working in. And what that means is that they have discontinuous absorption features, which you'll see in a graph in a minute, and also produce fluorescence X-rays when as a possibility of the way that the initial photon interacts with them. If you're interested in this, there's a very good web page here on the Siemens website, which I found only this afternoon. Just type in photon counting CT and Siemens and you'll find it, with some wonderful videos there explaining the difficulties of how this material is made. So looking at the way that our detector is read out, the electron micrograph on the left here shows you the circuit layout, and each of these little balls here is the connection between the integrated circuit and the cadmium telluride, which is going to be laid down on top of it. So within that 75 micron footprint here, Detectors have managed to squeeze in this circuit. So there's a charge sensitive amplifier which takes the puff of electrons and amplifies them to reasonable levels. And then there are two comparators. So if the charge goes above either of the comparator levels here, it will trigger the counter to count one photon. There's a slight interest here, which I'll explain in a minute, which is a retrigger unit, and there's also two counters for every comparator. So there's actually 4 counters in total for every pixel here. But what this allows us to do is to set the comparator level differently from on these two comparators, and that's very interesting for doing some work with either our third harmonic, which comes through our monochromator naturally, or just for rejecting background. So that little unit that was called the retriggerable unit there does this. If you can imagine a photon coming in, producing a puff of electrons, which will then go over the threshold level and produce a digital pulse out. If another photon comes in very closely behind it, within the shaping time of that charge sensitive amplifier, it won't normally get seen. This will only be counted as a single photon, and yet there are 2 X-rays that are coming in. So what Detectors have done here is they've limited the time for that pulse to be up, even though it may still be over the threshold, so that if the signal is still above the threshold after that first pulse has finished, it creates another pulse. And what that does is it stops the detector suffering from this, what we call paralyzing, where if you have such a high photon rate that you can imagine that in absurdum that the threshold is above, is set to 1 all the time, you just won't be able to count any more photons. And that's the red line in this graph here. But with this retriggering unit, they can extend that, and that's one of the real selling points of this detector for us. When we first approached Detectors with the idea of using a photon counting detector for synchrotron radiation work, they said, "Oh, there's no way we're going to be able to produce a detector that will cope with the speed of photons that you're coming in, because the synchrotron's such a bright source." But in fact, using this technique, and of course for us in medical imaging, we don't want to have such a high flux anyway, it's been pretty good. So all hats off to them. If we look at the quantum efficiency of the detector versus the energy, though, we can see the effect of these edges from the cadmium and the tellurium here. So one is every photon is counted 100% efficient. And as soon as you hit these edges, you lose some of the energy that is carried by the initial photon away from the converter material. And so your efficiency goes down. It goes down to about 80% in the case of somewhere around 30 kV, which is, of course, exactly where we want to work. So that is a problem, and it's an interesting fact that we can't get over, but it doesn't seem to have caused us too much of an issue so far. Even 80% efficiency for this detector is very good for keeping the dose down. So on to some of the characterization tests that we've done on the detector. As you may know from seeing some of the raw images, I'm not sure whether you have seen any of the raw images from the detector before, but the beam expander that we use is not entirely uniform. In fact, it's traditionally more of a banana-shaped illumination here. But that's about the best we can do. So this is we actually slightly better than this now, but this was an early 32 keV photon beam image, which was as uniform as we could get it. And you can already see some of the defects in the detector here, in the detector material, which is called the sand dune effect on these panels here, for instance. Some of the dark lines like this one here, for instance, are actually part of the optics and not the detector itself. But these threshold scan tests that we're doing, we're aiming to sort those out and to distinguish them. So we set the threshold on one of those comparators from 18 keV, which is the recommended point that Detectors told us to work with, down to the lowest, which is 4 keV. The reason that they want to use 18 keV is because if half of the charge from a 32 keV photon is shared between pixels, Detectors didn't want both pixels to trigger for one photon, and that would be the case if it was 18 keV. But as I'll explain in a little bit, if we ramp the threshold right down, we pick up more photons, and the effect of this multiple pixel hits per X-ray photon is not such a big problem. So from that collection of 100 images, we did some statistical analysis on it. We removed any systematic noise from those stacks by dividing the stack by its average. I chose a region of interest which avoided some of the what Detectors call the masked pixels. So these are pixels that have some problem, which will not be included in the image, but I managed to find a 128 squared region where there weren't any of these masked pixels, and then we look for trends in the flattened stack just to see over time whether the thing was stable, and then calculate the mean and the variance in that stack to look at the signal to noise and the linearity. And this was the results. We found that, as you might expect, starting with the recommended 18 keV threshold, this is a threshold versus standard deviation curve here. As we drove initially drove the threshold down, we actually found the standard deviation was decreasing. I still quite understand how that happens, but that's what we measured. And then the signal to noise ratio increases as you drive the threshold down, which is indicating that we really should be working with the lowest possible threshold to get the highest signal to noise. We then ran I'm not sure whether this is going to work, but this is a little movie here, which shows a rod beam. So a beam from the synchrotron that was deliberately faded top and bottom, and then we moved the detector, moved the detector through the beam, so it looked like this rod was moving down through the detector, so that in every pixel here would pick up every level of illumination of that rod beam, and then we can fit a straight line to that and look at the offset and linearity of a linear fit for every pixel in the detector. And this shows you some really interesting facts. Oh, here we go. So that's the process of just driving that beam down through the detector. So the gain map, if you like, so that's the slope of the fitted function for the detector is quite flat. The variation here is around about 2 or 3%, so nothing to worry about. You can see some of the inter-chip gaps here. You can see some of the defects that are more prominent in the material, the converter material here, but not too much of a problem. And again, the offset map, so this is where pixels don't start effectively counting, if you like, until they've got a few more photons, really does show up some interesting features of the material. So you can see these little diagonal features here are probably due to the way that the cadmium telluride was cut with a saw during the processing, and some of these things here are crystal defects in the cadmium telluride, but it looks much worse than it is. These are really only a few percent. I've just amplified them to show them up on this picture here. So in general, it's pretty good, and we're very happy with the performance. Now, I'm not going to go into this too greatly because this is not my work. This is Anton's work, who has been working very hard in order to find ways to close this gap here. So the big gap, the big horizontal gap here, is closed by actually moving the detector during the scanning process, so that for half the scan there's a black part in one part of the image of the object, and then for the other half that black line moves up, so we get half the number of photons in each of those two sections, which then Anton works his interpolation magic and produces this nice image which doesn't have those features in it. And the comparison that we've made or several months ago now was between the original flat panel detector that we used for the mastectomy work, which had quite large pixels, nearly 100 micron pixels, versus the photon counting Detectors detector with the 75 micron pixels. And I think you may have seen this already, but the quality of the image is clearly better on the Tiger images than it is on the flat panel. Now, the real way that we'd like to measure the detector quality is to measure the detective quantum efficiency, which is the kind of key parameter for measuring detector quality. And what that is the if you had purely Poisson distributed quanta, how many of those contribute to the image signal to noise? And this is a function of the spatial frequency in both the horizontal and vertical direction. And it's also a function of the noise power spectrum, and the modulation transfer is the function that everybody pretty much uses to compare the detectors, and that's what we want to try and measure. It's not that difficult to measure, and fortunately we had a couple of my colleagues from Italy over here some months ago who took the data which allow us to measure the MTF using a technique that we call the slant, what is called the slant edge image function. So we put a very sharp slant edge, obscuring edge into the beam here. We look at the edge spread function by which is super sampled because of the slant on this edge here. We turn that into a point spread function, and then we turn that into the modulation transfer function. And here's the result. So this is fairly hot off the press. For 4 different beam energies and driving the threshold down from some high value down to the lowest value of 4 keV down here, we can plot the number of counts per pixel. And as you can see, quite not unexpectedly, for let's say the 23 keV one, anything where the threshold goes above 23 keV, we start to run out of photons until they go down to 0. But interestingly enough, if you look at the differential of these curves here, you can get some sort of a spectrum from that, because what you're doing here is, as I say, looking at the differential between these 2 points as you move the threshold along. So, for instance, the blue one here, which is a 23 keV photon, you can see quite a nice peak at 23 keV, and this one here, peak at 40 keV. So we can actually see the energy of these photons. So it's almost like the spectroscopic detector that everybody wants for the future. From that, we measured the modulation transfer function, and here is the 10% point on the modulation transfer function curve as a function of the threshold energy here, and you can see that, as you might expect, that as the threshold goes up, the MTF F10 point does go down. So it gets better with the higher threshold, but the signal to noise gets worse. So if we look at the 35 keV beam here, the difference between the 17 keV threshold and the 4 keV threshold is not very much. So roughly speaking, our F10 for this detector is around about 55 microns. The other interesting thing about this is to wonder what we can do about the charge sharing, because if our photon comes in and creates well, photoelectrons and Auger electrons, they have a fairly short range. That means that the top 10 microns of that 750 micron converter is the bit that does most of the work. We can make some assumptions about the size of the charge that's created, the charge cloud that's created, and assume that it's some fraction of a pixel for the assumptions that I'm going to make in a minute. The characteristics of the converter are also quite interesting. So a 32 keV photon will penetrate about 50 microns into the cadmium telluride. The fluorescence photons that are created from the cadmium and tellurium have a much greater mean free path. So the likelihood is that these will escape, you know, maybe 50% of them backwards away from where the photon was interacting. So the charge sharing will happen near the top of the converter, and then the charge will be dragged down by the electric field to the electronics underneath, and near the edges of the pixels, especially, we will get fluorescence events which will move from one pixel to another. So it's not only the electron in the charge that's creating the multiple counts in the pixels, but also the fluorescence photons. I started working up a very naive model of this, because in order to do this properly, and I think our Italian colleagues have actually started working on this properly, you really want to do this with a Monte Carlo model, but it's quite a tricky process. And I think this, as I say, naive model will actually help us to understand what's going on here. So if we have a charge cloud that's with a half radius r here, created near the top of the converter, an electric field which brings that charge down to an electrode here, and the pixel size is p, or half pixel size is p. Then as you change the threshold, you can model the way that the charge is going to be shared between these pixels, and whether the pixel picks that charge up as a photon or not. So just working through the maths here, if it turns out if the half radius is about 1/10 of the half pixel size, so 10% of the pixel is covered by that charge, then with a threshold set to 10% of the maximum, the 17% of the times this pixel is hit will create a second hit in another pixel. But in order to see this properly, a couple of weeks ago, I tried something that I didn't think was going to work, but actually worked quite well. And that was to investigate this charge sharing using a very, very small X-ray beam. Because we have a synchrotron, which is highly collimated, and I have a tungsten collimator, which I can put in front of it, I could actually create a tiny little X-ray beam on the detector, and then move the detector across in 10 micron steps as I was collecting the image. And then I can change the threshold and see how the charge or the number of pixels that are generated changes. So I haven't finished analyzing this yet, but this is the sort of data we're getting. So these are the rows here are the positions position of the detector as it moves across the beam here, and the color shows you how many hits there were in each pixel as it moved across. So this may be another way of generating the modulation transfer function. So thank you very much for your attention, and I'm hoping there'll be some questions and any suggestions as to what we might do in the future.
Terrific, Chris. A very cool presentation, which even to the non-physics mind of mine was very understandable. So thanks for making it so clear. I can see. I thought they were questions, but actually they were claps. So
thank you.
So has anyone any questions for Chris? Can I just ask a simple question? Because obviously there's a huge amount of investment that goes into these detectors. You mentioned about their reliability, but through time, presumably they do fade a little bit in terms of performance, or not?
They are likely to fail. I don't think they will fade. So I didn't make the point that there's quite a lot of these detectors on the Synchrotron already, not for imaging, but for diffraction experiments. And we have had some reliability issues where after a period of time, some of the modules stop working. The one that we have, I think, is still in warranty, and we would probably be advised to take out an extended warranty on it because I know from my colleagues on the synchrotron that it's quite expensive to send it back to Switzerland for them to put a new module in and get it repaired. Mm-hmm. Having said that, of course, our detector doesn't get quite so many photons on it as the diffraction detectors, so we could be okay. But yeah, because it's a solid state system, I don't think it'll fade as such. I don't think that we will damage the material and create defects in it, for instance, and get it, get that horrible sand dune effect any worse. But what might happen, as I say, some bits of it might start to go wrong.
Okay.
And I don't know whether Marcus is online here, but he bought a detector, which is a Medipix-based detector, for instance, and that did have defective pixels, unfortunately, right in the middle of the array, which is where you do not want it if you're going to do medical imaging. It doesn't matter if it's off to the side, perhaps, but so I think he had to send his detector back to get it replaced.
Okay, thank you. Thank you, Chris. There's a question from Francisco Enriquez. Does the detector performance have a temperature dependence?
Yes, it does. And the system, so that's the cooling system we have here, keeps the temperature very stable. I've only seen it once it's up and running. It only moves by about half a degree, even on a hot day in Melbourne here. So it's really quite a good. It's a Peltier-based heat engine at the back of the thing, and then a water-cooled radiator, and the dry nitrogen to stop the parts of it freezing. But yes, it does have a temperature dependence. In fact, we were warned by Detectors that we should switch it on for about half an hour and let it equilibrate before we start using it. But I must admit, I haven't really tested that out.
Tim.
Hi, Chris. Thank you for the great talk. It explains something to me which I still haven't understood until today. I think I have one, not so much a question, but a comment. But I don't know, you may be able to take on that and explain it further. But you may remember that when I've done quite a lot of measurements of or estimations of the spatial resolution of the images collected with the IGA, I kept coming with the figure of 1.3 pixel in the best of the circumstances. And that kind of worried me because I thought, where is our single pixel resolution that we were promised? But lately, it turned out that it probably due to the settings of the software that I'm using. It seems that 1.3 pixel number is actually a single pixel actual resolution. So the situation might be better than I thought for a while. It looks like we may be actually getting something very close to 75 micron resolution. Yeah.
So when you say resolution, you're talking about the full width at half max, or
yes,
the half point on the MTF curve, or something like that. The 50%.
Yeah, I measure things on the MTF, but then I try to convert it into the point spread function. So it's supposed to correspond to the full width of half maximum of the PSF.
Yeah, yeah, that's so it doesn't surprise me. One of the interesting things that will be exposed in the future is if Yanis is working with this the third harmonic, which is 3 times higher energy, whether we see a significant difference in the spatial resolution at that energy due to the fact that the charge and the fluorescence photons may actually be going further. So that we will get, effectively a larger pixel per photon.
Mm-hmm. Right. Thank you.
Any other questions for Chris? I remember, again, this could be a very naive question, Chris, but in the old days of film screens and different things, for gadolinium oxysulfide and those sorts of materials, they used to add other materials in there as well to make them more sensitive to the radiation and so on. Does this happen with these sorts of detectors?
We don't need to. So in those film screen packs, the film was sensitive to certain part of the optical spectrum. So they put materials into the gadox, which would boost that, I think it was the green or the blue part of the spectrum in order to get the DQE up. But with these detectors, of course, it's not quite the same. The bit that's missing, I suppose, is going to be the electrons in the charge cloud. As they pull down through the material, they'll get lost in those crystal defects. And there's not much we can do about that except for hope that the manufacturers in the future are going to produce less defect crystals. So no, I don't think we can hope to improve our DQE by doing anything like that. The other thing that you can play with is the voltage across it, the bias. I would hesitate to go there at this stage because we could potentially wreck the detector if we started. I don't think actually we have that ability without talking to Detectors to change the bias. And I'm assuming that they've done enough work in their labs to make sure that the bias that we're using at the moment is good. The other interesting thing is that the material. So when I was working with cad telluride years ago, the material actually polarizes. So with a voltage across it, the defect electron gaps in it will get bigger and bigger over time. And so you would have to switch off the HT and switch it back on again to sort of reset the material. Detectors don't seem to it's either done automatically in this detector of ours, or they don't seem to worry about it. But yeah, again, I've not actually, like the temperature, I haven't actually tried measuring that yet.
Yeah. Thank you, Chris. Yakov.
Hi, Chris. I am wondering, you mentioned this capability of 2 thresholds per pixel, which I appreciated long ago. So my question is, when do you expect for your software to be able to capture 2 energies simultaneously?
Unfortunately, it's a little bit outside of our control. I talked to the Detectors guys last week, and the lab in America, which is running the EPIX driver for the Eiger detector, are working on that. So I would hope that it wouldn't be in the too distant future when it will be totally integrated into the system. So the way that we use it at the moment, you would just have 2 frames for every image that you capture coming out. In the meantime, for the work that you and I want to do, there are a couple of options. Yanis tried this a few weeks ago using a different part of the detector subsystem to read out those 2 images, each with a different thresholds. But there is another way of doing it, which I managed to get going last week, which is a slightly easier in a way. It's still not going to be easy to do a computed tomogram with it, though. That's yet to be tested, but you can run a sequence of images where each image has 2 frames for the 2 thresholds and get that out as a TIFF file.
Right. But can you manually run this sort of sequence of data acquisition with your, say, sample rotation?
I believe so. I don't
Okay.
see any reason why not, but it hasn't been tested yet.
Okay. All right. Thank you.
Thank you, Yakov. Francisco.
Sorry, I was going to ask one question, but then based on the last question that Jacob asked, is it really possible to actually use dual energy in these photon counting detectors?
Well,
Just
sort
based
of.
on what I understood is that you are defining like a timing in which you have your detector active and then you like kind of like turn it on and off. Then if you start having different energies, your pulse is not only going to depend on the let me just make it clear. So you were telling that when you have two photons, the pulse is going to be wider, right? And the system has like it's on and then it's off and then it's on and off again. So that's how you can count two. Then if you have different energies, your pulse is not only going to depend on the number of photons, but also on the energy.
Yep. So what happens? So yeah, this is a slight complexity with the system. Is that you have to tell the detector what the photon energy is, and it will load up a table into its electronics, which will govern how big that pulse is. So what we need to investigate a little bit more actually is how that works, because it's not clear from talking to the Detectors engineers that I know how it works anyway. But yeah, you're right. Actually that re-triggering unit, we don't really need that, because we're working at such low fluxes in order to keep the dose down that we're never going to get anywhere close to worrying about pile up. You know, the two photons landing one above the other. So I think yeah, as I say, Yanis has taken some data on this and had a look at it now, but it's very early days to really make any comment about it. And I'm planning as soon as I can to try this new method out that I was just talking to Yakov about as soon as possible. So what that does is, as you probably saw from the circuit diagram, is it creates an image with one low threshold and an image with a high threshold. And Detectors are saying, oh, well, if you just subtract the two, then you get, you know, an image of the photons that were in between. But I'm not sure that that's quite the way that it is going to work, because it's not the same as having a window threshold on each pixel, where it'll only count the photons that have a charge within that window. That's not what the Detectors Eiger does, but they can sort of emulate that by having these two thresholded images.
Yeah, right. But now the question that I was meant to be asking, so I think I do PET instrumentation, and 2 years ago there was like a lot of groups trying to get cadmium telluride based detectors for PET instrumentation, but now 2023 you don't hear anything about cadmium telluride in PET. So I don't know. I was just wondering whether you have some ideas or some insights on why.
Well, I know. So I happened to be at a meeting the other day where a guy from Siemens was there, and he was spruiking their cadmium telluride based photon counting detector for CT. I think they've got 100 or 200 micron pixels, but it's still a photon counting detector, and they think it's wonderful. Of course, they would, but you know. There is another material, cadmium zinc telluride, which did show promise for having better defect parameters than the cadmium telluride. I'm not sure where that's up to at the moment, but I don't think cadmium telluride is going to go away, especially if we can understand and then ameliorate these problems with the fluorescence photons.
Thank you.
Okay, it's now 5:01, so I think we've reached the end. I can see Yakov has his hand up, but can I ask you, Yakov, perhaps to send your question to Chris afterwards? So I think, again, a super talk, Chris. Like Tim, I learned lots, so thank you for that. And if we can put our digital clapping hands together to thank Chris for his excellent talk, that would be terrific. Thank you.
Thank you very much.
Okay, well, thank you, Chris, and see you all soon.
See you.